Well, good evening. Thank you all for joining us this evening in the California Water Colloquium, sponsored by the Water Resources Center Archives. I'm Matt Condolf, a member of the executive committee for this lecture series. I'd like to mention that all the lectures are videotaped, and the videotapes are available for loan. And after a few weeks, they also are available on the website in streaming video. So we are definitely up to date. But it's better that you're here in person. And it's a pleasure tonight to introduce Ned Andrews. Ned majored in geophysics at Stanford. And then he actually stayed on there for a master's in the same field. His advisor recommended that he go east for his PhD. So he came to Berkeley. He arrived the same fall as Luna Leopold did, after Luna retired from the USGS. And although Ned came in with the intent to study solid earth geophysics, he fell in with Luna and they became good friends, and in fact that influenced Ned, and he began a career in fluvial geomorphology and sediment transport studies. He already had an interest in rivers. He was a river guide for the Grand Canyon dories as an undergrad, and I'm sure that was part of how he got lured into the field. Since then, he's been a leader in the field of fluvial geomorphology from his very enviable post with the U.S. Geological Survey in Boulder. He's been a leader in studies of geomorphology and sediment transport in the Grand Canyon, the Colorado River. He's also done a lot of work at the interface between physical hydrology and biology. His thesis committee included Don Ehrman, and he's done a lot of work up at Seichen Creek looking at physical and biological interactions. One of his more enviable assignments was to establish and continue to be responsible for 34 stream gauges in the McMurdo Dry Valley in Antarctica. And Ned has also taken on some administrative responsibilities at the USGS. He served 2 5-year terms as research advisor responsible for all sediment transport and geomorphology studies at the USGS. So in that time, he's supervised 34 PhDs and $10 million program. So obviously he has to push a little paper as well as go out in the field and do interesting things. And I think tonight's talk is a wonderful example of the integration of different fields into some very interesting insights into the effect of ENSO on stream processes on the California coast. Ned?
Thanks, Matt. It's a real pleasure to be here. It's always great to come back where you went to school, to see a lot of old friends that it's been too long, and it's especially nice to have such a lovely day and be able to give this talk in North Hall. Back when I was here, this was the water archives was in this building, and I used to come over from geology to get the water supply papers back before all the stream flows and sediment transport information was online, and so I would harvest and get my daily dose of hydrologic data here. And so it's a real pleasure to come here and do it in such a lovely place. El Niño and ENSO are very familiar terms to the broader public and in the popular literature. And if you think back to just a couple of years ago to 1998, we had a very strong El Niño episode, and there was a great deal of press coverage. It was an item on regularly on Jay Leno. People heard about it at night. Los Angeles Times, in a 12-month period, ran almost 1,000 articles that mentioned El Niño in some context. There was a governor's conference earlier in the year after NOAA predicted the onset of an El Niño. Great deal of statewide interest. Vice President Gore came to California, had this great confab, and to get the state prepared for what was to come. So it's been an item, I think, that, it's one of the scientific issues or the climate issues that people are generally familiar with. Well, also we see this in the science, that there's a large number of papers. Scientists are in a broad number of fields, are very interested in what ENSO might mean for their particular field of study. And the reason is that beyond about 2 weeks, we have very poor predictive capabilities for what the climate is going to be. And then with ENSO, we have something that appears to be a broad global phenomena, to affect climate in many different areas, and that there is some consistency if you know the phase of ENSO, and I'm going to define what I mean by that in a little bit, but if you know the phase, you can make some predictions. There are correlations, associations with droughts in particular areas, heavier rainfalls in others, temperature anomalies or deviations from the mean worldwide. Well, given all this interest, you would think that water managers would be very interested and, in fact, using information about ENSO to help them with the various decisions that they make. In other words, that when you have a forecast of a particular phase of ENSO, that it would become parts of operational hydrology. Let's say reservoir management. You have a multi-purpose reservoir. There's a certain portion of the storage that's available for water supply and another portion that's allocated to flood frequency. If you know you're going into a period where there's going to be greater flows, the water supply issue is less of a pressing one, you could allot more storage space to flood mitigation. But in fact, following the 1998 El Niño, survey was done, very interesting study, except for maintenance, sort of preventive maintenance, things like cleaning out ditches, buying more sandbags, preparedness things. Water managers didn't use it at all. And out of about 35 or so that were interviewed statewide, about 40% didn't think that the forecast of an El Niño had sufficient certainty to it for them to take any action. Basically, they didn't believe the forecast. About 30% said that they had legal constraints or legislative directives, established policies that did not allow them to adjust their operational plans. And about another 30% said, well, we considered it, but it didn't really seem like there was any benefits to changing our operations, that there were marginal benefits. And in addition to sort of what I've been referring to as operational hydrology, you can think of a number of other situations where if, let's say, 2-3 months in advance, you were to know that floods are more likely or less likely, that there's going to be a higher proportion of sediment moved than is usually moved, or a smaller proportion, that there's a whole variety of things that we could possibly benefit and increase our chances of success. So one of these might be stream restoration projects. Another one would be endangered species issues, habitat issues for endangered species, or perhaps build strategies that would tend to promote native species over exotic species. So we can start thinking of a whole range of types of manipulations, activities that we would like to do in streams to achieve a desirable end that could be benefited if we were to have some kind of prediction, not 2 weeks in advance, but a few to several months in advance of what is going to happen. And I'm going to start out with a particular example today, but then I'm going to, where we can sort of consider how the phase of ENSO affects flood frequency and sediment transport, how we could use this, and I'm going to just sort of explore how these flood frequency varies across the state and sediment transport in the context of this particular example. Well, I have some fine colleagues that I want to recognize. You know, one part of dealing in this is that you cut across a number of fields, and so I've really benefited from my association with Ron Antweiler, Mike Dettinger with the USGS in San Diego, Dan Cahan with Scripps Institute of Oceanography, and Marty Ralph with NOAA at the Climate Prediction Center in Boulder. Well, this is Matilija Dam. It is in the headwaters of the Ventura River, just east of Santa Barbara. If you're familiar with the Santa Barbara area and the mountains behind there, Matilija Dam is up into that area. And in this photograph, it looks benign and rather inviting at first look. But you can already see something that might catch your eye and say, well, that's odd. Notice here what this is kind of cut down, and these are notched. Well, the dam originally went all the way across like that. And Matilija Dam was made improperly. The concrete was made with aggregate that came from marine sediments. There's a fair amount of what's called opalite in it. It reacts with the alkaline in the cement. This is a well-known process of opalite-alkaline reaction, and gradually the concrete disintegrates, not over a period of a year or two, but over a period of decades. It has much less than the normal lifetime for concrete, and this dam is in the process of failing. It's on the state engineer's watch list. You can actually see these survey marks here on the face of the dam. Quarterly, they go out and measure the deformation of the dam. The thinner sections at the top were actually disintegrating and were cut off, partly as a just to see if they could do this. And the dam is deforming. It will last a few years, but not several decades. Well, there's another problem, and maybe you begin to see it back up here. Matilija Dam is full of sediment. It's chock full. And you can see the dam down here notched. It's about 30 feet lower than it used to be. There's about 10 million tons of sediment in this deposit that have accumulated. And this is not unusual. There are a number of dams in Southern California, throughout the state, in fact, that are full of sediment. But the fact that the dam is failing makes this the poster item for dam removal. Something has to be done. It's not something we know a whole lot about. And I should say, a question that probably some of you are already thinking, well, what's in this sediment? Well, it turns out that, and this has been, cores have been drilled throughout this sediment, and there's no heavy metals. There's no pesticides, there's no herbicides. I mean, they're at background levels. So there is not a sediment contamination issue here. It's about 40% silt and clay, 25% or so, almost 30% sand, and about 10% coarser gravel. Well, there's been a fair amount of study over the last few years about what do you do with this sediment, because it turns out that removing this dam is about a $10 million, $15 million effort. It actually seems to be easier than you might think. The big issue and the big expense is, what do you do with all this sediment? And you can think up a variety of different ways that you could do this. But it's a pretty substantial deposit. And I should say, I mean, 10 million tons is not, it's sort of an average for a dam deposit that's full. I mean, this is a typical amount of sediment to deal with. Some of you probably you're all familiar with these large earth haulers you see on the highways. It's kind of a half pipe trailer. Those are 20 cubic yards, about 38 tons. To remove this deposit, that's 300,000 truckloads. And if you're familiar with the area near Ojai, that's a truckload every 90 seconds, 8 hours a day, 52 weeks a year for 11 years. It's a huge disruption, and it's very expensive. County commissioner, although this is one of the items studied, or one of the approaches studied in the feasibility study, he just said that's political suicide. There's no way we're going to truck it out. You could also think up of various combinations, though, of perhaps not trucking it on highways, but putting it up into gullies up here, perhaps stabilizing parts of the deposit, using a slurry pipeline. There's a whole variety of things. And of course, one obvious one is to say, okay, let's just cut the dam down a little bit at a time. And I say a little bit is that you cut it down so that as you lower the dam, a certain portion of sediment gets is now above the lip of the dam and is susceptible to be eroded and carried downstream. Let's just cut the dam down at some kind of an acceptable rate so that we control how much sediment goes downstream, and let the river carry the material out and downstream. Well, it turns out that this is the cheapest way to do it. It's about, it's still going to cost $10 million. The other scenarios go up from that to over $100 million. So it's a huge difference of expense. There's also benefits of letting the river carry the sediment out. And this, again, is a kind of a common situation, particularly in Southern California, but elsewhere throughout the state, is that we have dams like this filling up with sediment. Then there's a coastal plain, and we've got beaches eroding away at the shoreline. So letting the river erode sediment out, carry it downstream, 17 miles, deposit it on Ventura Beach, that would be a real benefit. It could use the sand. But there's also a liability here. This deposit, as it sits, 10 million tons, represents half, little over half, almost 60% of the channel capacity from the dam 17 miles to the ocean. In other words, if you took all this sediment, spread it out down the channel, it would take up 60% of the channel capacity. People live there along the river. If you lose channel capacity here, the flood risk is exacerbated. The Ventura River can no longer pass the design floods. And this issue would kill it. If you cannot present a a compelling way to move the sediment from the dam down to the sea, this isn't going to be accepted. And just to elaborate a little bit on how the sediment would get off. I mean, the dams, as you saw, was up in a tight, narrow canyon. And relatively, if you cut the dam down, you expose 10, 15 feet of sediment above the level of the dam. It's susceptible to be removed. Relatively small flows, a few hundred CFS to 1,000 CFS, would be able to erode the dam deposit, carry it downstream a mile or two through this the lower end of this bedrock gorge, and then the channel spreads out. It widens into an alluvial reach. The slope flattens somewhat. And there's quite a bit of groundwater recharge, percolation into the stream bed. And so you have a real risk that that sediment can be eroded off the dam deposit and not carried all the way to the sea, and it would accumulate in the channel. Vegetation gets established during a period of when there are no substantial flows, and that then when after 2, 3, 4 years, when you have a large flow, that you would no longer have the channel capacity, or that it would be reduced enough that it would accelerate the risk. And so this is the downside of guessing wrong. So if you cut the dam down in October and then you don't get a good flow in December, January, February during the high flow season, you get the sediment moving out the dam deposit but then accumulating in the channel, not making it to the sea. Well, this is daily sediment loads in the Ventura River. Now this gauge is down at the sea. So this is going to give us some indications of what kinds of flows are going to carry the sediment, have been carrying the sediment from the area of the dam all the way down to the ocean. This is kind of what we're really seeing here is what is the frequency of flows that are large enough to carry material down to the beach where we want it and not let it accumulate somewhere below, between the dam and the coast. And it starts 1948, goes to 04. Notice these values here: million metric tons, 2 million metric tons, and these are basically days. The lines gets pretty small here. What you see is that there is just a few days every couple of years that move a significant amount of sediment. That you can go for stretches of 5 and 6 years and there really isn't any movement. And overall, you would say, well, this is totally unpredictable. If this is the game you have to play, you're going to lose. Okay, you're the water manager. Think of the situation or the perspective from the water manager or the head of Ventura County Flood Control. It's October. How much does he cut the dam down? Now, if he's very careful and just cuts it down a little bit, well, it would take forever. So, if he says, well, I'm just going to let a little sediment dribble out at a time, the dam's going to be there. I mean, well, it would fail before they got all the sediment out. But if he cuts it down too much, most of the time it's going to sort of dribble out of the dam and accumulate downstream. And that's just shown by this statistic that comes from summing these. And notice, I mean, there are some days here. This is actually the flood of record. There's almost 2 million tons moved in a single day. Well, there's only 10 million tons in the reservoir, but it's so unpredictable. you wouldn't know when to do, when to cut it down and liberate. So you really can't take advantage of it. So we have 90% of all sediment transport in the Ventura River over the last 55 years has occurred in just 135 days. So 2.5 days per year on average, but it really happens by, it's 5, 6, 7 days every 4 years or 5 years, something like that. It's unpredictable. And if you think about this sort of in kind of a betting game, if you had to bet on this, you would lose, except if you can get some kind of an edge. You need something that improves the odds. And that lies up here with this number, 135. It turns out that over this 55 years, 124 of those days have occurred during an El Niño condition. There's been very little sediment during non-El Niño conditions. And so that then gives you this edge. And what I want to do now is explore how El Niño influences flood frequency in California coastal streams, what that influence is, how it varies along the coast, and the sediment transport. And then I'm going to apply this back to the issue of Ventura. And I guess I want to say, I'm using the Matilija Dam and the movement of sediment as an example, but I hope that you can, that you have some other, hydrologic operational issue of your own, and you're thinking about it, because we're going to find that it actually comes out to be kind of equivocal for Matilija, really, whether you can build a scheme to let the river cut away the sediment in a feasible amount of time. But depending upon the issue, what you want to achieve, and where it is in the state, I think you can build viable schemes around ENSO phase and have a good risk-reward ratio for it. I just want to finish up with one, if you can realize what this is or recognize what this is Matilija Dam right here. The water's going over the top about 2 feet deep and plunging 160, 170 feet. The sediment has filled up the major outlet works. They can release about 10 to 20 CFS from an auxiliary over here. But after that, the dam just fills up and it just pours over the top. It was raining hard at the time this picture was taken, not surprisingly. And it's a spectacular sight to see. Okay, so what is ENSO? Well, it stands for El Niño Southern Oscillation. And I'm going to show an animation here in just a minute about what ENSO is. El Niño refers to warm water on the coast, right along the coast of South America here. Here we have the coast of Peru, Ecuador, the equator, Central America here. ENSO is a tropical phenomenon. It's important to keep that in mind. And already you can see kind of an odd situation. These warmer colors are warmer water. El Niño refers to sea surface temperatures. Why do you have all this cool water right at the equator, where just north of it and just south of it, you've got warmer water? It's an odd situation, but this is the normal situation that you see. And this is, would be a La Niña condition. I'm going to actually show 2 years of the 1997-98 ENSO event in just a minute. What happens here is you normally have easterlies off the coast of South America flowing this direction. It carries the warmer surface water to the west, and you have colder, deeper ocean water upwelling along the coast of South America. So that's the normal situation that we have. And now you'll see, when I start the animation, that you'll see warmer water start developing. Well, what happens is that the pressure difference, which is the southern oscillation between Darwin, Australia, and Tahiti, which are the gauges that are used, switch, and then you have net westerly flows that then carry the warmer water to the east and allow it to accumulate. Well, this higher than average sea surface temperatures here on the equator next to South America is an El Niño, and the significantly colder temperatures than average is La Niña, and then you have a neutral condition. So we'll see this animation, and it's about, it's animation, but it's based upon actual measurements of sea surface temperature, and it runs for a 2-year period, and it'll cycle through it twice, and it's about every 2 weeks. You'll see the warm water start developing here. This is now the summer. Now it's into the fall going up. This is the wet season. This would be the peak of El Niño, and when the coast of California would be most affected by it. Now it's waning, and La Niña conditions are returning with colder water accumulating along the tropics. Well, so you can take these, the combination of the sea surface temperatures here and the wind directions, as well as the cloudiness and wind shear along the tropical zone, and you can make up a what's called a multivariate ENSO index. Is something developed at NOAA. I find it more useful than the just using the straight Southern Oscillation Index. And the main thing to know here is that if you're familiar with Southern Oscillation, negative Southern Oscillation is El Niño, but positive ENSO is an El Niño. And what we do is we just divide this into sort of arbitrarily a third. The highest third of values are El Niño. The next third is neutral, and then we have La Niña conditions. And so this is the values, monthly values, that I'm going to use then to correlate with flood frequency in places. But you'll notice also already in here that this period here prior to the late 70s looks rather different than the post-70s period. And there is wide recognition that there is a low-frequency oscillation in El Niño, and that it is not a constant. And part of our problem is we really don't have enough information. But it does appear that this phase of ENSO that we've been having since the late 70s is now changing. So as we go forward, just keep that observation in mind. Okay, well, you take that kind of index. This is one of the early results. You take that long ENSO record and you correlate it with annual stream flows, and you say, well, do I see an effect? Is there a correlation between, let's say, the ENSO index and higher stream flows or lower stream flows? And so this is annual stream flows, And you see a broad pattern here of a correlation in the south. In other words, as ENSO goes to a larger value towards the El Niño value, you have higher stream flows. There's a large area here in between that's almost neutral, no particular correlation, and then a pattern in the north. So this gives you kind of a seesaw. El Niño you'd tend to find it wetter in the south, La Niña drier, and then flipping. As I go forward, kind of remember this structure that we see here, this pattern, and these correlations. Because as you go to look at different aspects of the hydrologic cycle, whether you say precip, evapotranspiration, extreme floods, extreme droughts, you see different patterns. It's not radically different. You still see this seesaw, but the structure, the gradients along the coast, and the correlations change dramatically. So I'm going to start out here with, there's 41 gauging stations that I went and selected that have close to 50 years. I tried to find gauging stations with 50 years of record. In some cases, I took ones to fill in an area, these two right here. And I haven't named all the streams. I just picked the ones that people may be familiar with. There's Nacimiento here as well, that have a little bit shorter than 50 years of record, or excuse me, 55. I had a 55-year record of El Niño or ENSO to work with, so I looked for gauges that had close to 55 years of record, that had no regulation, no appreciable regulation of their flow, and minimal stream flow diversions. These are the available records. There's actually 41 that I've used here. And then of these, about 20 have sediment records. And Ventura is right here. The Ventura River and Matilija Dam is right here. And then I'm also going to show you a record from Yosemite on the Merced River. Okay, well, so what does this stuff look like? And I've showed this, I sort of, the next slide is also, it shows the same data, but I wanted to show it to you once without any lines on it, without really any interpretation. Here's this ENSO index indicating ENSO phase. This is El Niño over here, greater than 0.5. This is La Niña, less than 0.5. Here's the annual peak. This is San Juan Creek near San Juan Capistrano. And you know, when you first look at that, you say, doesn't look like a whole lot to me. Is there really anything to dig out of this? And the answer is yes, there is, but it is kind of subtle, and you gotta work at it. It turns out there is going to be a correlation through here, somewhat better than the stream flows. That's one way of looking at it. But the other thing is that you'll notice that actually some of the highest flood peaks here don't occur at the highest or the strongest El Niño. We're going to see that the strength of an El Niño doesn't affect the flood frequency. Whether it's an El Niño or not an El Niño affects flood frequency, but whether it's a strong or a weak El Niño really has no effect. So let's look at the next slide. And we fit this relationship. Remember, this is down the area where the correlation with stream flow and ENSO index had an R squared of about 0.3. Well, here floods is 50% more. So there is that kind of correlation. But if you just break up into the El Niño floods and the non-El Niño floods, you see that the correlation is much less, and in fact with floods essentially disappears. Well, rather than looking like some continuous process, I look at this and I say, well, it's really two populations. It's not something that we correlate, but there is a distinction between those, and that's the way I'm going to treat it now. And if you take these now and say, the issue is really, is it an El Niño or not an El Niño? And then it's two different populations. And you compare these, the mean of the non-El Niño floods, and these are just the highest flow, instantaneous flow each year that I'm working with here. And this, the average flood during an El Niño year is about 15 times the non-El Niño year. It's a huge difference. It's very striking. And here, 8 of the 10 largest, there's actually 3 right here, 8 of the 10 largest floods on this stream are under El Niño conditions. Well, you take those two populations and you do a flood frequency analysis on each of them. Here we have exceedance probability. This is the 50% exceedance. Over here, this is just about 25 cubic meters per second. It's really not a lot of water. You go up here, the same mean annual flood, 15 times as much. It's a huge effect. And even if you go to a relatively rare flood under a non-El Niño condition, be the 2% exceedance, the one that's exceeded or equaled or exceeded 2% of the time, the equivalent of a 50-year flood under El Niño conditions, or excuse me, non-El Niño conditions, it comes back to it's the average under an El Niño. So the most extreme flood recorded under non-El Niño conditions is just an average during an El Niño condition. Well, so that's what you see in the far south. The reason I started into this, looking at other gauges, is, of course, that the Ventura gauge is somewhat problematical because you've got this reservoir that's been there. It's gradually been filling up. And then in the meantime, since that reservoir was no longer usable, they built another larger one. So Ventura record itself is affected to a substantial degree by, or at least complicated. But I've gone ahead and I did a flood frequency analysis in the same way for Ventura, and you see that even with these complications of adding reservoirs and reservoirs filling up over the period of record, there's almost, it's about a 7-fold difference. At any exceedance probability, the flood's about 7 times greater during an El Niño period than a non-El Niño period. Well, let's go further north, but one thing to note here, as I go through these, you're going to notice that the distance between the two relationships is, I've plotted them so that there is a distinctive difference. But if we just go back one, you'll notice the log scale here, and what's going to happen to keep the separation, the log scale actually expands. So as we go a little bit north, actually to just north of San Francisco, Niño River, there's no difference. So this is the 0 point, but you notice whereas that first diagram I showed you of the correlation, there was a huge portion of the California coast that was just kind of blank, no correlation. But in fact, there's a very, very well-defined gradient up along the coast, and it's gone to 0. And then you go a little bit north, and it's flipped over. When you get to, now this is the Umpqua, which is the first major basin in northern, in southern Oregon. At a given frequency, the El Niño flood is only, it's about 70% of the non-El Niño. So now it's depressed. This is the part of that seesaw, but you see that whole section of the coast has now has been filled in with a structure, and there is a correlation and significant relationships with El Niño. Well, This is just a normalized, I've calculated a normalized El Nino index here. And if, at a gauge, if the way that this normalization works, if El Nino floods are very, very large, this index would go to 2. So you see here we are in the south, right along the Mexican border. You'd have El Ninos everything. And as you go north, the influence of El Nino decreases, and actually you have down here the non-El Nino floods are more important. These are two little interesting gauges right here, Soquel and Corralitos. There's a great story going on, but I'll leave that to questions if anyone is interested. So, I mean, look at the R squared. Latitude explains 90% of the ratio of El Nino to non-El Nino floods. It's a huge effect. So what do you think happens here? I mean, that's a pretty strong relationship. Anyone want to guess? It's gone. And you can, you know, there's a little bit of scientific humility here. Trend doesn't go on forever. And if you go into Washington, the next big basin is Queets, and it's back up to 1. There's no difference between El Nino and non-El Nino floods when you get into southern Washington. So even though there's a correlation with mean annual runoff in Oregon, remember that gets into there's a negative correlation. When you're talking about floods, even though we've had all this detailed structure here along the coast, you get into southern Washington state, and yes, there's a correlation with mean annual runoff, but with floods, there isn't. Okay, so I've been talking all about the coast, and some of you are wondering, well, tell me about the rest of the state. Why are you ignoring the rest of the state? Well, here's this index again. This is just like the first El Nino, non-El Nino slide I showed you for San Juan. Here is the annual peak discharge. This La Nina, El Nino. Here's the distribution. I've identified these as snowmelt peaks and rain on snow peaks. Well, let's just look at the snowmelt peaks first. There's no correlation. And in fact, this is true. Once you move in from the coast, you see no effect of ENSO phase on flood frequency. I've used this one example, but I've done them all the long-term records that are unaffected by regulation in the Sierra Nevada, in the Mojave Desert. There's no effect of ENSO phase on flood frequency, on the snowmelt. I have to be careful when I say no effect, because there's a little curious detail here. You got these rain on snow peaks. And this is very curious. I mean, they're important because they're the largest flows of record. And this is true throughout the Sierra Nevada, that the largest floods at a location are the rain on snow events. Well, what are those? That's when you get 6, 8, 10 inches of rain at 10,000 feet. Those have to be the warmest storms that come into the state, you know, once a decade, the warmest, wettest storm that comes in. And look when they come. They come during the La Nina phase when you've got cold water in the tropics. And in fact, statewide, during during La Ninas, the state mean temperature is a little bit less. So when the average wintertime temperatures are a little bit colder, you still get the warmest winter storms that ever come on shore? Well, I've put this to my friends at NOAA, and they have some ideas about how that happens, but it's kind of an intriguing little detail that goes on here. You have to be careful that we say that ENSO has no effect, because in fact there does seem to be a very consistent signal here that you get these extremely warm storms, rainfall at 10,000 feet during a colder than average winter. Well, I said I was going to talk about sediment transport. And you can also make up a number of hypotheses, or reasonable hypotheses, that you should have higher sediment at a given discharge, whatever it is here, 10 cubic meters per second, that you ought to have more sediment moving during an El Niño than a non-El Niño. Okay, how might these work? Well, one of them is based on a fire cycle, that you have an El Niño, vegetation grows, becomes very established, you have a period of dry, the 2, 3, 4 years, the vegetation dries out, it burns, releases lots of sediment, it's sitting there until you get the next El Niño storm. Well, you don't see it. And I've just used this one example, but I've looked at all 20 records, dug through whether there's any difference between the concentration of sediment that's transported by flows during an El Niño year, non-El Niño, neutral. There isn't. Again, it's an interesting topic exactly how that happens, because I do think that fires do release sediment, but also as you go through an El Niño year, so you may have a release of sediment that accumulated from fires or an extended period of dry, but as you go through an El Niño year, of course, you're getting higher and higher antecedent moisture, so at some point you start having more mass movements. You might have release of stored channel sediment early, but then higher supply from mass movements later in the season, so that sitting downstream at your gauge, you don't see anything, or you don't see a difference. Okay, so I just about done here. This is comparing then the sediment records, and the amount of sediment transported at these stations varies tremendously. There's, these are kind of granitic streams. These are more sedimentary rocks. There is a fair amount of variability, but this just compares the proportion of sediment that's transported during various phases of ENSO. And down here at San Juan, which is the first stream I talked about, 96% of all sediment moves during an El Niño condition. About 3% during the neutral condition, less than 1% during the La Niña condition. And as you move north, this is in a zigzag pattern, you see this, it's a very, it's a continuous gradient, but there is a increasing significance of the La Niña and the neutral, and a decreasing proportion of the sediment is carried during El Niño conditions up to the Smith River. And then actually you can, very similar results here. Then as you're getting into the Nehalem, that's going back to no effect whatsoever. Okay, so just to return for a few minutes to what's happening in the Ventura River. I proportioned out, this is over the 55 years of record, the proportion of the flow that occurs during an El Niño year, neutral year, La Niña year, and the amount of sediment. But these averages are misleading, particularly for the purpose of removing sediment from this reservoir deposit, because the distribution of annual sediment loads is highly skewed. And you're going to see here, I mean, here is this, you would say that the average that you might be able to or that's carried by an El Nino year is 1.4 million tons, and neutral La Nina about 120,000. But those averages are in fact much larger than the median flows. So, I think what a sediment man, someone, again, our manager of the flood control district would want to look at is not the average, but an exceedance probability for sediment transport. How much sediment would you expect to be transported during these years? And so that is shown here. This is an exceedance probability. So it says there is 2% of the time this load, a little over 1 million tons, is transported during a non-El Nino year. And you see at the extremes, they tend to come, the two distributions come together, and this is one of the observations. Virtually all the large floods and virtually all the sediment gets transported during an El Nino year, but not all El Nino years have significant floods or sediment transport. So sometimes there's virtually nothing transported. I mean, you see here's 20 tons. There's essentially nothing happened in that year. But look at the 50% exceedance. This would be there's a 50-50 chance that you're going to move more or less than this amount. During a non-El Nino season, there's a 50-50 chance, 7,000 tons. And remember, our deposit is 10 million. Doesn't do much. But look up here. This is a factor of 10. The 50% exceedance during an El Nino year is 100 times greater, 700,000 tons per year. But the median is about half of the average. So this is about really what you can say you can have a reasonable expectation of getting about that much sediment moved during an El Nino year. So you could build a plan of cutting the dam down, notching it, and releasing sediment and minimize the risks of accumulation by using something like these amounts. And when you do that, you get a figure like 20 years. If the sequence of El Niños that we've had since 1978 to 2000 persists with that. Okay, well, there's one last slide I want to point out. I finessed one point here. And I can imagine, well, I know that it's been causing Bill problem. Because you're saying, okay, well, this is how much sediment's moving, but you want to add more on top of that. How do you know it's going to move that additional amount? And I think that there's certainly situations where it wouldn't. But this is just a close-up of what the bed of the Ventura River looks like. A lot of large cobbles. And it would be another full-hour lecture to go through how you might come up with how much additional sediment you could put over this stream bed. But the short answer is that you can, this is about, I'm showing a patch of sand here. That's the subject of this photograph. If you include these areas over here, sand makes up about 15% of the bed surface area. And if you were to locally increase the percent of sand coverage to about 25%, you could double the sand flux that the river would be carrying at that discharge. So, whereas in a sand bed channel, you'd have to aggregate a great deal of material in order to double the flux. I think that in the Ventura River, you don't have to do that, and that a relatively modest increase in the amount of sand coverage on this bed would substantially increase the downstream flux. So, just to wrap up, I mean, you see that there are obviously other issues. How does the sediment get out of the dam deposit? I mean, there are significant issues. You cut the dam down so much. How is the river actually going to erode the deposit? How rapidly is that going to happen? And how much of that moves downstream? But for the question of, can we develop an edge? Is there a way that we can reduce this variability or uncertainty of when flows will occur of a substantial magnitude, a sufficient magnitude that the sediment that's released from the dam can be carried downstream to the sea and not accumulate in the channel? And I think that in terms of that question and this location, in other words, Ventura, because you see as we go much further north, we lose that edge. But on the other hand, you might argue that as you go to a regime with much more predictable flows, you don't need the edge anymore. I mean, if you had a situation where you knew what the flood was going to be each year, then that would be the ideal situation for using river flows to erode sediment. Thank you very much.
I came late, but Matt said, I guess you didn't address the issue of course, what's happening this year, especially in the Ventura River where they had some high flows. And there was a weak El Nino, but now people are debating how weak it is. And, you know, what's happening this year, I think, is real interesting because of the preponderance of what I guess I would call cutoff lows, cutoff circulations that usually aren't associated with an El Nino. And I just wondered, can you comment on what we've observed this year and how it fits into your model?
Well, I did intend to touch on that. Maybe I didn't emphasize it, or it was after you or before you came. I showed that you can have very large floods during El Nino years that are relatively weak. If you look just within the El Nino phase, the relative strength or weakness of El Nino has no effect on the flood frequency. And that's what we had this year. And that also relates to 1998. That was the strongest El Nino of record, or the second, depending upon how you structure them or compare them. And it was not a particularly heavy runoff year, particularly in the south. Whereas this year we had a relatively weak El Nino, but we still had very large floods. And I think, so there is this common idea, I know, that you get within an El Nino phase that the relative strength of El Nino is significant, but you don't see that in any of the records. You get just as large floods during weak El Ninos as you do as strong El Ninos. And a very sort of quick cursory explanation. You know, a lot of these storms are carried by these subpolar jets. And they're relatively narrow and well-defined, maybe 300-400 kilometers across. And during an El Nino condition, those subpolar jets can come on shore in the south. And the issue is sort of not how far they are north, but whether they're landfalling at your particular location or at a particular location on the coast. So it's not sort of a gradual thing. It's either there or it's not.
Actually, I want to kind of follow up on what you just said.
Thanks. Have you been able at all in your research to resolve how cold water at the equator then forces more precipitation north of Fort Bragg, California?
No, I mean, that's one of the challenges. I go to my colleagues at NOAA who work on the teleconnections between what's going on in the tropics and then how does that actually deliver moist tropical air to the coast. And there's a couple of different processes. I can direct you to a lot of, this is a subject of a lot of work because, we have this tropical phenomena, but then how does that, how do those conditions get translated into the mid-latitudes? And it's an important issue. I don't mean to minimize it, but it sort of goes beyond my expertise.
Can you tell the story of the 2 data points on the bottom left side?
Okay. So one of my themes that I tried to put out was there's interesting little twists and there's details in this ENSO signal that can vary along the coast and by location. And this is a rainfall record from Punta Blanca, just at the south end of the Santa Lucia Mountains, just north of Hearst Castle. And there's two records here. And at the bottom, this is the wind direction. So here's due south. This is the wind direction, and this is the total precipitation that was accumulated when the wind was blowing from that direction. So they've got a wind profiler that's measuring wind direction, and they're accumulating a hundredth of an inch at a time, or a millimeter at a time, and this is down on the coast, and this is up on the slope of the Santa Lucia Mountains, so you have a higher orographic effect. But the main thing is, look at the direction. This is due south, and this is east of south. The highest rainfall, the largest proportion of the rainfall, and this is during the 1998 El Niño season, came on shore from a little bit east of due south. Who would have thought? I would not have suspected that. And if you want to check this out, it's partly that the coastline has a major east-west component, and so that you can have storms from the actually coming on shore from the southeast and making landfall. Well, it turns out that during La Niña conditions, the storms don't come on shore from due south. They come on shore from the southwest. So there's a rotation. Not only is there a change in the number of storms that come on shore at this location between El Niño and non-El Niño, there's a directional change. And what happens for those two streams, and Barry will recognize this, for storms coming on shore due south, here is the San Lorenzo Basin, and it fit right where it should by latitude, but Soquel and Corralitos are over here. And so even though they're in a portion of the coast where the El Niño storm should create or be associated with slightly larger floods than non-El Niño, because of the direction and the aspect of those two basins, they're in the rain shadow of the Santa Lucia Mountains. And The La Nina storms and neutral storms that come on from the southwest do not encounter that rain shadow and go straight on shore. And those of you who are familiar with it, if you just sort of remember these basins, you know, Pescadero is pretty wet. Certainly, I mean, San Lorenzo is wet, particularly the western part of it. You get into just the eastern part of the San Lorenzo Basin, it gets drier. Soquel is a little drier than that. Corralitos is very dry. And so it's not just storms coming on shore, but the direction at which they come on as well has a significant effect.
I want to understand your principle of how to use this information. I think very clear idea that you get the most out of the reservoir, you should have it set at least when you have anticipated outcome. And then when you talk about volumes, do you mean to imply that what's come out of the past is an indication of what would come out when this reservoir is released? You said like 40% of the reservoir sediment is silt clay.
60%.
60%, great. If you had a lowering of the reservoir and a lead event, it seems to me that you could get a much bigger load coming out of the reservoir than what you might have had in the river in the past. So I'm wondering if I get carried on this. I don't think you were applying, but I don't see if you were. So well, I got 1.4 million tons out of this event. Something like that. It seems like you get a much bigger load out of a similar discharge event because you have so much fine sediment being put in the river. And by and large, still clay is supply limited, even in large rivers.
It would depend, I mean, you say much larger, it depends how much you cut the reservoir down and therefore how much sediment you expose. And kind of what I suggested without, you know, much argument or support was that you could increase by, let's say, 50%. Or perhaps as much as 100% over what has occurred. Essentially the concentration of silt, sand, and clay could be increased by 50 to 100% over what it has been. And so that increase represents the amount of sediment that you could get out of the reservoir deposit. That's why I'm suggesting that yes, it is. Remember, I mean, like when I showed, you know, one day is 1.8 million tons. That was actually less than it would have been if the reservoir hadn't been there. I mean, the sediment was being accumulated. So the question comes up is. You can certainly go back up to where it was, the sort of the natural or pre-reservoir condition. How much can you surcharge it over and above what it has been transporting and still not have an objectionable channel adjustment, something that you find objectionable, you know, for whatever reason.
I guess so. It's the common thought, of course, that silt clay is usually not a limiting amount of sediment, so you can until you get to extremely high concentration. So if you have the normal security of a reservoir that's silt clay farther out from the reservoir now, if you have that, then perhaps you get a lot more in a shorter time frame.
Perhaps you could. The analysis that I chose to show here is consistent. I mean, the loads that I showed you were for total suspended loads. I have them also for sand. I could have given sand loads. So for simplicity here, I gave the you know, what has been the total suspended transport and compared it versus what is in the reservoir, the total amount in the reservoir. Could have done essentially, you know, what is the sand flux? And you would have seen a very similar kind of relationship for the sand flux. It just would have been lower. And then you would look at just only the amount of sand in the deposit, and it would basically, everything would have been 30% less. So it's a consistent comparison that I've used. You know, if you wanted to look at just the sand, you know, it could have been done that way. You get exactly the same result.
Do you have any comment on how this would be affected by climate change?
Oh, yes. Oh, I was waiting for that question. Well, you know, I did allude to there appears to be this low frequency in ENSO, and that's, again, we just don't have enough long-term data to really resolve that. There's, you know, we don't know, we don't have a long enough record of ENSO to resolve what that might be, but it certainly appears to be significant. And there's really no way to go forward on that. Two ways of kind of approaching that particular question. I mean, one, of course, would be global warming. How might we expect ENSO to change with global warming? And of course, the way we usually do this is, or the way that it's commonly approached now, is we have a global circulation model. You increase greenhouse gases and you run it. Well, the models don't catch all of the details of ENSO when we run them for 20th century conditions. So if you run them for the climate that we know, they do, the models do, the coupled ocean atmospheric models do give you an ENSO oscillation, but it tends to be more on a 2-year period rather than a 5 to 7 year period. The amplitude is not right. And so the global circulation modelers are, when you ask them about this, they're very cautious about what might be the effect of global warming on the frequency or the magnitude of ENSO. One of the other things we can look at is not sort of modeling and going forward, but look back. There's a very interesting study of lake deposit in Ecuador, where there's a very, very strong El Niño signal. During an El Niño condition, you get very heavy rainfall. You have debris flows going into this lake. And when you core the lake deposit, you can see the El Niño conditions very well exposed. Well, in that core, you go down to about 5,000 years ago, and there's no more El Niños. It disappears. And so the early Holocene we know was warmer than today, and this oscillation, southern oscillation, El Niño, La Niña, might not have existed at a generally warmer time. Not a very satisfying answer. A lot of interest in this, but I don't know that you can argue. I mean, to me, no one has presented a compelling conclusion and support for how the frequency and strength of El Niño would change with a warmer climate.
Well, I think we should wrap it up there, and thanks once again to Ned for a great talk.